Hi, my name is Muhammad Abusaria, and I will be giving a presentation on the principle of resonance. To kick off my presentation, here is a brief overview of what I'll be talking about. I'll be discussing the video that got me interested in researching this topic, describing some terms needed to understand resonance, as well as explaining it, giving examples of a specific type of resonance called mechanical resonance, presenting an argument dealing with the reason that the Tacoma Narrows Bridge collapsed, and finally ending the presentation with the solution engineers came up with to fix the Tacoma Narrows problem. The spark that got me interested in choosing the topic of resonance was a video called Tacoma Narrows Bridge Collapse, Gallopin' Gertie. The Tacoma Narrows was a suspension bridge in Pierce County, Washington, that was opened to the public on July 1, 1940. This bridge was significant in that it was considered one of the best bridges at the time, and it was also the third longest bridge in the world. Then, on November 7, 1940, the bridge collapsed due to the effects of a strong gale. The gale, which was traveling at a speed of 42 miles per hour, caused the bridge to oscillate uncontrollably, thus decreasing the stability of the recently built bridge. This bridge that was made of cement and steel looked as if it was a piece of paper flapping in the air. The strange oscillations continued until the bridge finally collapsed. The reason as to why the bridge collapsed is still disputed to this day, but one theory concerning this catastrophe is that it was caused by a phenomenon called resonance. Before I start explaining resonance, I'll describe a few terms that are needed to understand it. The terms are energy, amplitude, and frequency. Energy is defined as the ability of an object to do work. Two basic forms of energy that we usually consider are kinetic energy and potential energy. Kinetic energy is the energy of motion, and potential energy is the energy of position. Amplitude is the maximum height a wave obtains. In the case of the bridge, the amplitude would be the maximum vertical height it would reach when oscillating. Frequency is the number of repeated occurrences over a set period of time. That set period is usually taken to be a second, and it is given in the unit hertz. With all of these concepts in mind, I can begin to explain resonance. Resonance is defined as the tendency of an object to vibrate or oscillate at greater amplitudes when another source emits a frequency that matches the natural frequency of the object. The reason that an object vibrates at greater amplitudes is because of an object's ability to store energy. To better understand this, we take the example of a child on a swing. In order to make the swing go both fast and high, we usually push the swing in a rhythmic manner. We are creating a frequency and slowly providing energy for the swing to store. As we continue to push the swing, it stores more and more energy, and the swing obtains the ability to reach maximum height. A damping force exists, however, that will slow down the swing almost instantly once it reaches this maximum height by taking away energy from it. In this case, the damping force would be air resistance, friction, and tension. This is why swings eventually stop when no one keeps pushing it. But essentially, you'll only achieve maximum amplitude with resonance. This statement then leads us to the question of what happens if both emitted and natural frequencies don't match. So the maximum amplitude is only obtained during resonance. If the emitted frequency is smaller or larger than the natural frequency of an object, it will not be able to produce the same effects as those seen with resonance. To get a more vivid idea of emitted and natural frequency, we take the example of an opera singer trying to shatter glass. So this can sometimes be done by accident, but if the singer wants to shatter the glass on purpose, then she would have to tap the glass in order to figure out the natural frequency of the glass. She would then sing at a frequency that is similar and eventually shatter the glass. Here is a video that demonstrates a similar concept to what I just described. Going back to our question, when the frequency is lower, it will obviously not provide as much energy in order to produce large amplitudes. As for frequencies that are higher, they will cause the system to receive more energy, but at the same time it will decrease the energy of the system much faster. It is as if we are helping the damping force decrease the energy of the system. So we can conclude that if we want a system to oscillate to its greatest heights, then we must match the natural frequency of the system. But in most cases, we don't want that due to the dangerous effects that resonance can produce. Mechanical resonance is a type of resonance that deals with mechanical systems. A mechanical system is taken to mean any physical object. There are many incidents such as the Tacoma Narrows Bridge collapse that occurred due to this phenomena. One such incident was the collapse of the Nimitz Freeway in San Francisco, California in the year 1989. This collapse was caused by resonance that occurred with an earthquake that happened at the time. Earthquakes are considered to be dangerous due to the damage that they can cause, but surprisingly, they emit frequencies as low as 1 to 10 Hz. The dangerous part about earthquakes, however, is that they not only emit one frequency, but they emit multiple frequencies, which creates more of a chance for there to be a match between the emitted and natural frequencies. The freeway itself was built on a layer of mud, and when geologists took the frequency of that mud section, they found it to be an average of about 2.5 Hz. The earthquake that came with multiple frequencies emitted frequencies close to 2.5 Hz, and led to the same ill fate the Tacoma Narrows Bridge experienced. There is also another famous example with soldiers crossing over a bridge during war. The soldiers were marching in step over the bridge and created a frequency that matched the natural frequency of the bridge. The bridge eventually collapsed due to oscillations, leaving soldiers stranded on the other side. This is why soldiers march out of step nowadays when they are crossing over bridges. They do not want to add enough energy to the bridge to allow it to oscillate. These are all examples of mechanical resonance, but the most famous example is considered to be the Tacoma Narrows collapse due to the magnitude of destruction caused. There is, however, an argument if resonance was the actual cause of the collapse. There is an article that tries to prove how the explanation for collapse of the Tacoma Narrows Bridge can be misleading in many undergraduate physics textbooks. The writers argue that engineers conducted research on how the bridge collapsed and they found differences in their explanation compared to that of what many undergraduate textbooks try to convey. Engineers were able to calculate that the frequency of the gale at the time was actually 0.2 Hz, while the natural frequency of the bridge was 1 Hz. Resonance could not have occurred at such values, and so there must have been another reason for the collapse. The reason was a fundamental antisymmetric torsion mode. Basically, what this means is that the bridge collapsed due to one unstable vibration that happened 45 minutes prior to the collapse. This vibration had a negative damping force that created wind forces within the bridge that moved the structure out of place. This phenomenon is called self-excitation or aeroelastic flutter, and the author of the paper goes on to show how the bridge fell due to self-excitation rather than forced resonance, both through verbal and mathematical proof. Whether or not this phenomenon was caused by resonance wasn't the big concern, but how to solve the problem was. The problem was not the wind. A bridge of that magnitude should be able to withstand that kind of speed with ease. They found out that the problem was with the design. When they made the bridge, they had closed the sides on the deck, which didn't allow for passage of the wind. This way, the wind was able to affect the bridge heavily. That is why when we drive on bridges today, we usually see that the bridge sides are not closed, but they are in fact open. This is to allow for wind passage and to make sure that the wind doesn't have much of an effect on the bridge. So, the Tacoma Narrows Bridge collapse was not caused by residents, but I was still glad to have researched this topic. I was intrigued by the new info I discovered on the topic, and I found it to be of the utmost importance, especially to engineers. People usually think that brute force produces the greatest effects, but resonance proves otherwise. I found that to be intriguing, and I hope you did too. Thanks for watching.